Hi, everyone. A little more organic chemistry, and a little is all we got left. We're almost done with the second semester of organic chemistry. And here we are in our last of the key concepts. So, key concepts, unit 5, part 3. Yeah, we're going to break this video up into two pieces, one about lipids and a second one about proteins. And that'll end our course. Then specifically, it'll end the unit on biochemistry. Okay, lipids. Well, here's just a rundown from an organic chemist point of view about lipids. And of course, take a biochemistry class or a biology class to learn more, because there's more to these molecules. But here we go, kind of a preview from an organic chemist perspective. Lipids. One definition is that they're simply biological molecules that are not insoluble in water. So that's pretty broad. So there's a lot of biological molecules that don't dissolve in water. Think about fats and oils and things that are greasy. Okay, but when you inspect those biological molecules, you're going to find regions of the molecules that in fact could dissolve in water. They're going to have sections of the molecule that are hydrophilic. And if you look at the breakdown or the origin of this word, hydro refers to water and philic means loving. We've seen that philic ending before in nucleophilic, right? Nucleophiles, molecules that seek the nucleus. Okay, so these will be functional groups or portions of a molecule that are seeking the water. And it's just describing polar compounds that dissolve in water or parts of a molecule that are polar. Then there's other types of molecules or other regions of a molecule, other functional groups of molecules that are hydrophobic, the water fearing. If you have a phobia, you have a fear of something. Hydrophobic means you have a fear of water. And so we apply this term to molecules or portions of molecules that are greasy, waxy, oily, things that don't dissolve in water. Or another way of saying it, things that are nonpolar compounds. Cool. So we got molecules that like water, molecules that don't. Is life really that simple? No. Things are not necessarily binary, right? So we got amphipathic. Amphipathic. And the amphi reminds me of amphibians. You know, creatures that live both in the water and on the land. They can do both. Amphi means both. Pathic means, I guess, applying to this. I don't know. I should have looked up the term there. But here, amphipathic refers to molecules that have both polar and non-polar aspects of their molecule. As you look at the whole chemical structure, you can find regions of the molecule that are polar, hydrophilic, and you can find other sections of the molecule that are greasy, non-polar, hydrophobic. Okay, and many biological molecules that are lipids share these amphipathic properties. And we'll see several examples. So I'll make sure to highlight the amphipathic properties of these biological molecules. Oh, and then what are we going to do with that from a predictive point of view, right? Chemistry, we like these guidelines and rules, not too many rules, more like guidelines that allow us to make predictions, accurate predictions. So if you have a chemical structure and you're identifying the hydrophobic and hydrophilic portions of the molecule, after you do that, you might be able to make an educated guess as to whether the molecule is or is not soluble in water. And so if you have molecules that are largely overall polar, then the prediction would be it should dissolve in water. If you look at it and say, oh man, look how non-polar this molecule is, well, that's probably not going to dissolve in water. So the more portions of the molecule that are polar, the more likely it'll dissolve in water. That's sort of the guidelines. And then we got here a little thing here that says if the hydrophobic part dominates, the molecules don't dissolve in water. So that's what's going to be true of most of the lipids. You're going to find regions of their chemical structure that are polar. But the majority of the structure is going to be non-polar. And the non-polar part, the hydrophobic part, is going to dominate and prevent those molecules from dissolving in water. Hey, and here's some common lipids, phospholipids for making the cell membrane. Tricylglycerides, they're the molecules that make up olive oil, corn oil, canola oils. things like that. Steroids are lipids, estrogen, testosterone, and the anabolic steroids, and cholesterol is a steroid. And then we have fat-soluble vitamins. And here's some examples. Vitamin A, D, E, and K generally don't dissolve in water. They dissolve in fat, or they're stored in the fat. Oh, here's a structure of cholesterol. And just like the video two videos we saw on carbohydrates, you don't have to memorize structures in my class. You'll be given structures, but then you have to analyze them or talk about them or draw a new structure from the given structure. So here's cholesterol. And sample problem, just to illustrate what you might have to do on exam is, hey, here's cholesterol. Circle and label the hydrophilic and hydrophobic parts of cholesterol. Okay, well, let's start over here on the left. Here's an alcohol group. Is that hydrophobic or hydrophilic? Hydrophilic is water loving. Hey, alcohol group, don't you hydrogen bond to water? Yes, you are very hydrophilic. That's the polar part. And if you inspect the rest of the molecule, we only find carbon and hydrogen, double bonded carbons, but the only atoms present in the rest of the molecule are C and H, pure cane sugar from Hawaii. Sorry, the old jingle from C and H sugar comes to mind. And that's how I remember when C and H bond together, it makes a non-polar covalent bond. CNH, pure cane sugar from Hawaii. C bonded to C is the same two elements. That's also a non-polar covalent bond. So this is stuff that you should have learned in Gen Chem and hopefully sound familiar to you. And now, recognizing that the entire remaining portion of the molecule after the alcohol is C's with H's, every bond is non-polar, the entire rest of the molecule then is non-polar greasy. But that's not the term we were looking for. Go back and read the term. We're supposed to circle and label with hydrophilic and hydrophobic. Okay, so hey, does cholesterol dissolve in water? No. A little itty bitty alcohol group over here is trying to help the whole molecule dissolve in water and fails. The entire portion here is greasy, waxy, hydrophobic. No, cholesterol does not dissolve in water. How many stereoisomers of cholesterol are possible? Okay, that's going way back to first semester of organic chemistry. Again, this is biochemistry from the other way around. This is biological chemistry from an organic chemist perspective. So one of the things we do in organic chemistry is look at chirality, stereoisomers. So how do we predict how many stereoisomers are possible? First, we count the stereocenters or the chirality centers. And those usually are carbon atoms with 4 different groups, right? Not necessarily 4 different atoms, but 4 different groups. The carbon could have a methyl group, an ethyl group, a propyl group, and a butyl group. I know those are all alkyl groups, but they're different. And that counts as making that carbon with 4 different alkyl groups a chirality center. And then the number, can I use hashtag here for number sign? Number of chirality centers or stereoisomers is equal to 2 to the n power. So n is the count, the total number of chirality centers. And that becomes your power, an exponent to 2. Okay, this is actually a very kind structure. You don't always get nice structures like this. Why are there wedge and dash bonds? That's why this molecule is very kind to us. It's drawing. Every time there's a wedge or a dash, that's because there's a chirality center. So right here, this carbon has a wedge bond to an OH group, top half of a ring, bottom half of the ring. Are the 2 halves of the ring identical? No, this carbon has two H's, and a methyl. This has two H's, no H's, and no methyl. It has a double bonded alkene there, a carbon-carbon double bond. So this is a chirality center. It's got 4 different groups. Top half of the ring, which is different from the bottom half, different from an alcohol. Where's the 4th group? A hydrogen on a wedge bond. That's dash bond. Okay, there's one chirality center. Here's another wedge. Convince yourself, kind of inspect. Yeah, there's 4 different groups. That's a chirality center. Here's a dash bond, hydrogen going away, and there's 4 different groups. Here's a wedge. Here's a dash. Here's a wedge. Here's a dash. There's another dash. 1, 2, 3, 4, 5, 6, 7, 8. Cholesterol is to the 8th power. Yikes. Let's see. That's 2 to the 2 times 2 to the 2 times 2 to the 2 times 2 to the 2, right? Add up my 2's. So that's 4 times 4 times 4 times 4. That's 16 times 16. And I don't know why I know this, but it's 256. 256 isomers, oh my gosh. And only one of them is cholesterol. So flip this one, you would get the epimer. Yeah, you use the term epimer for things that are not carbohydrates. Epimers just apply to, hey, how these 2 molecules differ? Well, they can differ in one stereoisomer or stereocenter. So if you change this to a wedge, that is an epimer of cholesterol. And it's a different molecule, not cholesterol. Do that with any of these, or 2 of these, or 3 of these, or 4 of these, 5, all the different variations, and you can crank out, theoretically, 256 variations of all these stereocenters. And out of all those, nature makes one of them. That's crazy. No, that's just remarkable. Oh my gosh, nature's amazing. Okay, cholesterol. One example of a lipid. Another example, tricylglycerides. Okay, so on my kitchen counter, I got a big bottle, not that big, bottle of olive oil. Also been using some avocado oil. Heard there's some health benefits to that, so I thought, why not? If you could look into the bottle and actually see the molecules that make up olive oil, canola oil, avocado oil, what would we see? We would see these molecules are called triacylglycerides or triacylglycerols. Looks like I didn't put it in here. I forget which one's the older term. I don't know. It might be, I don't know, that's just a guess. Anyways, 2 terms describing one type of molecule, one class of molecules. These molecules that make up the oils start with glycerol, great for making soap bubbles, but it's 3 carbons. Every carbon has an alcohol group. And then you take 3 individual fatty acid molecules, a fatty acid. It's actually a good name. Acid stands for a carboxylic acid. And the fatty part stands for something greasy, waxy, oily. Yeah, just an alkane. So just a straight chain alkane here, no branches, carboxylic acid at one end. And then glycerol has 3 alcohols. You bring in 3 carboxylic acids, and going back to unit 3, no, I think it was back in unit 1, we talked about one of the reactions of alcohols with carboxylic acids with an acid catalyst. You can make an ester. Well, 3 alcohols are in glycerol. Add 3 carboxylic acids, you make 3 esters in this one molecule. And now we have one example of a triacylglyceride. You don't have to use the same one. You can choose different lengths of chains. You can actually add some double bonds if you wish. Notice that the double bonds that are in this drawing are all cis. Nature has favorites. Nature prefers cis double bonds in fatty acid chains if she's going to put some in there. What else do we need to know? Okay, some terms you need to know. Oils, that term oil, if you're applying it to a biological molecule and not fossil fuels. An oil, from a nature point of view, are triacylglycerides. that happen to be liquid at room temperature. So if you put, I haven't tried it. I wonder if you'd put some olive oil or something like that in the freezer, see if it hardens up. Coconut oil, is that right? One of those oils that you can get at Trader Joe's, if the temperature of the store is too cold, it'll harden up and turn into grease, this waxy white grease. Okay, so that's frozen, that's a solid. So go to room temperature. Guess we have to agree what temperature would that be. Some people like the rooms colder than others or warmer than others. So it's kind of a loose term, but typically if it's sitting on the countertop out in the room and it's a liquid, then those triglycerides are classified as oils. Now, if you think about, gosh, butter, margarine, those are the same molecules or similar structures. A glycerol molecule connected to 3 fatty acids by 3 esters. But those are solids: butter, margarine, lard, shortening. If you ever made cookies with shortening, we make our Christmas cookies out of there, sugar cookies with a little bit of shortening. Well, probably a lot more than I'd like to think. Those are classified as fats. Triglycerides that happen to be solid at room temperature. And so that brings us to our first point here. Wait, why are some liquid and why are some solid? Well, it has to do with these cis double bonds here. So this is a convenient way to draw the chemical structure, but it's probably not the most common shape or conformation of the molecule. Remember doing chair flips back with cyclohexane? We were inspecting the molecule. Or remember Newman projections? We looked at the shapes of molecules. Yeah, because shape actually influences functionality and the way molecules interact in nature. So this triglyceride is drawn this way for convenience, so we can clearly see, oh yeah, I see a chain, I see a chain, I see a chain. Oh, and this one has double bonds, that's kind of cool. But over here on the left is more to perhaps the actual structure, the actual shape you might encounter in nature. Straight chains have single bonds that can wiggle and bend, so that straight chain may actually put a kink in itself. The double bonds, though, have a cis chain. Do you get a sense? I do, that this chain is, this part of the molecule is in its right shape, but then it kind of kinks backward. It's kind of weird. It's like, I feel like, ooh, the molecule's a little more relaxed. Now it's in this shape. That cis double bond kind of puts a bend, a natural bend to the chain. It really doesn't want to be straight like this. It wants a bend or turn about this. And every cis double bond has a natural kink or bend. So over here, the molecule is just kind of bending on itself. Okay, so that's a key point. That wasn't just, oh, that's kind of interesting. No, this is important. We got terms to describe molecules like this, and we're going to come back just a second to liquid and solid. But I'm also following the what's this called? The format, the organization of this slide. And I see this point here. So let's not miss anything and go here. What are we talking about here? This is a lowercase omega. If you've taken some physics and looked at Ohm's law, you might be familiar with the uppercase form of omega. Omega is the last letter of the Greek alphabet. So chemists and biologists have adopted that letter to mark the end of a chain. You know, end of the alphabet is omega, so hey, use that letter for the end of a chain. Remember the old Greek lettering system that we had? The most important functional group next to it is the alpha carbon, then beta, zeta, eta, theta, all that good stuff. And then we just depart from that and say, well, don't do it that way. What if we want to start counting from this end, the other end? Well, that's the omega chain. I'm sorry, the omega end. And now use numbers to go locate what you want to see. So here's the omega end, that's the first carbon at the end of the chain. Here's the second one, here's the third one. So an omega-3 fatty acid has a double bond starting on carbon 3 from the end of the chain. So have you heard good things, health benefits from omega-3 fatty acids or omega-6? Yeah, they're talking about, ooh, is this one a 6? No, probably not. Here's the omega N. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is an omega 9 fatty acid chain. Okay. What else do you need to know? So if you're taking notes, make a note that you do need to identify oils and fats from the chemical structure. And I'll explain how to do that in a second. You also have to know that oils are liquid at room temperature and fats are solid room temperature. You also have to know what to do with omega. It's counting from the end of the chain. Other terms, saturated, actually, you know that term already, right? A saturated alkane is one that doesn't have any, has only saturated alkane. It's got the maximum number of hydrogens, that's what I'm trying to say. If you have a molecule that has a degree of unsaturation, then there's either a ring or a pi bond present. Okay, for triacylglycerides and fatty acids, a degree of unsaturation is going to specify a cis alkene, or I guess more generally just an alkene. If there's only one, then it's monounsaturated, 1 degree of unsaturation, 1 alkene. Polyunsaturated means 2 or more. All right, so let's test this out. Here, do we find it? Let's just classify. What's this chain? Is this a saturated, polyunsaturated, or monounsaturated? Yeah, that's a saturated fatty acid chain. There's no alkenes present. On the screen, can you find a monounsaturated fatty acid? Okay, so the key word there was fatty acid. So the fatty acid chain is only this portion of the molecule, and there's only 1 alkene here. So this chain is monounsaturated. Can I abbreviate it that way? And then here's 2 or more. So this fatty acid chain is polyunsaturated. And then, can I ask you to find a polyunsaturated triacylglycerol? I used the old term, didn't I? I can't spell. Glycerol. Still can't spell. Okay, so a triacylglycerol is the whole molecule. And so in this whole molecule, there are 4 alkenes. Yeah, and all you have to do is find 2 or more. What kind of triacylglyceride is this? It's a saturated triacylglyceride. Are there any monounsaturated triacylglycerides here? No, there's only 3 triacylglycerides. And this one over here is also polyunsaturated. Yeah, we'd have to draw a molecule like this one, and in an entire molecule, there's only 1 alkene. And that would make for a monounsaturated triacylglyceride. Okay, so read the question carefully. On the exam, on the final exam, is it asking for a monounsaturated fatty acid? That's where you inspect each of the chains, because each of the chain was derived from fatty acid. Or is it asking about a triacylglyceride? That's where you have to look at the whole molecule. Okay, liquids and solid, how can you predict it? Well, these kinks in the chains caused by the cis alkenes make these molecules oddly shaped. Gives them weird structures. Like there's a, just look at this molecule here. This is kind of big open, there's a bunch of gaps in here, big open structure. And this is kind of dense. The chains are kind of stacking, packing next to each other. Up here, we got the saturated one, and all the chains could, they don't have to, but they could straighten out. And now they could stick through van der Waals forces, right? These are non-polar hydrophobic portions of the molecule, non-polar portions of the molecule. Non-polar molecules stick to other non-polar molecules by the van der Waals forces, London dispersion forces, induced dipole-dipole forces. Okay, and so these chains can actually stick together. But more importantly, you can have 1 fatty acid molecule. So if I draw, I'm not going to draw it. It's too much to draw. Think about one of these molecules sticking to another one of these molecules, sticking to another one. It's possible they could all line up their chains and stack nice and tightly together. And if they can do that at room temperature, they're going to form a solid. But if your tricylglycerides contain some cis double bonds, it doesn't have to be every chain, right? This molecule doesn't have a cis double bond, but the whole molecule is classified as an unsaturated tricylglyceride. You just need one, maybe more would help, but at least one. That's going to put a kink in the chain. And it's going to make it more difficult for these chains to all line up and stack tightly together. They'll be more loosely packed. And if they're more loosely packed, they're not stuck to their neighbors so much. They're able to slide around and be liquid at room temperature. So there's the key. The more cis double bonds within your collection of triacylglyceride molecules, the more likely it'll be an oil. More likely they'll be liquid at room temperature. So here we go. Oils are liquid at room temperature because they contain more cis alkenes. The fats don't have a definition. It's just the opposite. Fats are solid at room temperature because they contain fewer cis alkenes. So think about hard butter or margarine. If you ever try to put some butter on a piece of toast or bread and start ripping up your bread because the butter was so hard. Yeah, so that butter, the really hard butter, contains a lot of tricylglycerides where most of them do not have any cis alkenes. Most of the chains are straight chains, saturated chains, and they're stacking tightly together. Think also, next think about some of those butters that are soft spreads, shed spread, or some of those soft spreads, maybe even the kind of squirt out of the bottle, right? And you can tell it's not an oil, like shed spread soft butter. It's still hard, but it's creamy, it's softer. Well, what's making it less hard, it's still solid, but not so firm, is that it has some more of those tricylglycerides have some cis alkenes in there. There are some molecules that have some kinks in them. They're not stacking tightly together, but overall they can to form a solid at room temperature. What I'm trying to say here is that everything isn't black and white one way or the other, right? So it would be incorrect to say fats are all saturated. No, fats are just solid, and the more saturated the triglycerides are, the more likely they'll be fats and solids. But it doesn't have to be 100% saturated to be a fat, right? You have some chains, a small minority of chains containing cis alkenes, some kinks, but the majority of them are saturated, all alkanes. Most of the molecules stack together, and then they'll allow it to form a solid at room temperature. Whereas something like canola oil or olive oil, there's a higher percentage of molecules containing cis alkenes that prevent the molecules from stacking together at room temperature and keep it liquid. There we go. Cool. All right, let's talk about trans fats then. Trans fats, that's an alkene that's, zigzaggy. It's not one of nature's favorites in terms of triglycerides. That's where you actually put a, you have your fatty acid here connected to the glycerol. So the rest of the fatty acid, whoa, not what I wanted to do. Oh, I went this way. And then as you put in your chain, the fatty acid chains, if you have a trans double bond, well, that's going to help keep the chain straight. It is a degree of unsaturation. So technically this is an unsaturated fatty acid, but it's in the trans conformation, which allows a chain to be straight. It maintains this nice zigzag orderly structure and allows these chains to stack tightly together. So that's not very healthy because trans fats are more likely to form solids. And now fats actually taste pretty good. Our bodies are really good at breaking down fats and getting energy out of it. And our greedy little bodies are like, let's store some fat for later. We might be hungry later. And that's why we put on the weight. So easy to put and store these triacylglycerides, store these fats. And now, you know, in our diet, we eat these fats. And how do you get nutrients from the digestive system to the rest of the body? Through the bloodstream. So we got to transport, the body's got to transport these triacylglycerides, which are lipids, which are insoluble in water, through the bloodstream to supply all the body's needs, because these are energy sources. So what do you want? So a long discussion, getting to a point where you have to think about triacylglycerides in the bloodstream. Do you want them as oils or as fats? Do you want them as little tiny oil droplets, if you will, or little pieces of butter, little particles of solid? No, no, no. You don't want the fats, right? Fats are solid at room temperature. You want them plugging up your arteries. You want these little tiny droplets of oil that keep on moving. There you go. And so the trans fats are more likely to form solids, more likely to contribute to arterial plaques, these, you know, collections of fats on the inside of arteries that plug and clog like a greasy pipe. No, so avoid trans diets in your diet. Avoid trans fats in your diet because they're more likely from solids. Where do trans fats come from? Because nature usually doesn't make those. Maybe there's some plant that does. I don't think so. I think most of them are cis. Nature's kind of looking out for us. People have done it. So there's a little blurb here about the economics that lead to the industry, you know, the food industry creating trans fats, not intentionally, but just in the money-saving effort. But anyways, have you read any of your ingredients packages and seen the term partially hydrogenated? I think I got one down here. Yeah. Partially hydrogenated vegetable oil or soybean oil or hydrogenated oils. So way back last semester, remember hydrogenation? Catalytic hydrogenation, adding hydrogen gas to a double bond over palladium and carbon to make it a single bond. Yeah, so take a look at this. This video is getting a little lengthy. If you want to know why people decide to do that, but they have done that. And the problem is that if you change all the if you change all the cis alkenes of these oils, then it makes a very hard fat, right? Fats are solid. So you don't want to change all the double bonds to single bonds. You only want to change some of them. So you don't hydrogenate all of them, you partially hydrogenate. And so people wanted to make these ingredients. They don't want, I don't know, these are cookies. So they don't want greasy, oily cookies, but they take the oils, take away the alkenes by hydrogenating them, put in single bonds. So now they're more firm, more like butter. People like the feel, the texture, the taste of cookies that have lard and shortening in them. Sorry, they taste good. And here's a cheap way to get to those fats that are good for cooking. The problem is, in the process of partially hydrogenating, you can make trans fats. And the government says as long as your trans fats are less than 0.5 gram, you can round down to 0. So be a little careful. And though it says 0, what it really means there's less than 0.5 gram of trans fats present. Okay, enough said. Let's move on to some other lipids. What else we got? Oh, let's do something with these triacylglycerides. So take some olive oil, take some animal fat, I don't know, lard, whatever. Add some sodium hydroxide or the ashes of fire contain potassium hydroxide. Throw in a pot of water and you can make soap by saponification or base catalyzed hydrolysis. You can break all these esters, the recovered glycerol, and then the anions of the fatty acids. And then those molecules actually make up soap. You can make soap, saponification. And so now these molecules are going to get pretty big. Some of them have double bonds, the unsaturated fatty acids would, but we're just simplifying our structures. Instead of drawing the proper number of carbons, because it can vary, they're usually even numbers of carbons in these chains. Let's just draw these amphiphiles. What? Because they're amphipathic. They're both polar and non-polar. They're both hydrophilic, water-loving, and the non-polar ends are hydrophobic, water-fearing. It can also, well, here is a phospholipid. How about that for making up cell membranes? And it's derived from tricylglycerides. You clip off or hydrolyze one of the fatty acid chains and you put on a phosphate group, or you can modify the phosphate. Nature has some cool tricks here. But now you create a larger polar head group here, hydrophilic portion, but the majority of the molecule is still hydrophobic. So this molecule really doesn't dissolve a molecule. It doesn't dissolve in water. Same is true for this one, right? Got the carboxylic acid anion in. Ooh, anions are very polar. There's a negative charge out here. This portion wants to dissolve in water, but the majority of the molecule is greasy, oily, waxy. It's hydrophobic, just an alkane. So you put a bunch of these molecules into water, and whether they do, they don't like to dissolve. So they kind of either stand on the surface of the water, trying to get their greasy tails out of the water because they fear the water, hydrophobic, or if they're in the water, kind of stir this rapidly, get them go inside, they'll group up. Or each of these anions of carboxylic acids will put their polar head groups, the carboxylic acid negative charge, facing the water, which is, the rest of this solution, and they put the greasy tails in the middle to escape the water because they fear it so much. And this three-dimensional structure is called a micelle. I don't know if you can see that. It's pretty small type. I got another picture down below. And then what's cool is you can take the phospholipids, and because of the bulk of the double tail, double chain, when they group up, it's hard to form a micelle because two chains in here gets pretty crowded. So they form these liposome structures. The tails are all getting away from water, and the polar head groups will actually form an inner surface where you can have water inside here, and the polar head groups on the outside of the surface, and they can interact with the water out here. And that's starting to look like a cell. Those of you who've taken a little biology know the phospholipids make up cell membranes. That's just a natural phenomenon that those molecules do. And then these two-dimensional drawings don't do justice to the true shape, right? So the micelle, that's one way you can draw it, but this is a better way of drawing it. It's a three-dimensional structure. And this is half of micelle. We just cut it in half so you can see the inside. And here's a liposome, what might eventually turn into a cell. That's kind of cool. Okay, before I get too far into the biology of this, which is really cool, let's just make sure we understand the chemistry. I might ask you to draw a micelle on the exam, or I might ask you to draw a liposome. And what I'm expecting is something that looks like these drawings here, these 2D structures, this one or that one. And so what you need to do is understand that, hey, if I give you a certain molecule to build a structure from, reduce it to this simple drawing. So maybe I'll put carboxylic acid with 10 carbons on it. And I might say, oh, there's another one with a double bond on a chain of 14 carbons. Well, just draw both of them with a circle and a line. That's a shortcut. And then just whatever molecule I give you, count how many chains there are. Do I have a circle with one line? Or if I give you one of these molecules or something similar, oh wait, there's 2 chains, so I better have a circle with 2 lines. And if you're building a structure with 2 lines, a double chain, you're going to go after a liposome. But if you have a single line, you're going to go after a structure that's a micelle. Cool. Phospholipid bilayer, liposomes. Cool. So if you take the phospholipid bilayer and you kind of circle it up, take these ends, bend it together, wrap it around, right? You'll actually construct the liposome. And from a liposome, you can get to a cell membrane or a plasma membrane. And now we're going for a full circle here. Remember when we talked about cholesterol at the beginning of this video? I don't think I pointed out the fun fact. Cholesterol, why do we have it? Why is it present? Why is it such a problem? My doctor says, watch your cholesterol. Well, cholesterol is an important biological molecule. This crazy shape is going to help keep the cell membrane fluid and flexible, right? Okay, let's go back to triglycerides. What's the difference between a fat and an oil? I don't know. Yeah, you do. Oils are liquid, fats are solid. Oils like olive oil, corn oil, canola oil, and then you got your solids, butter, margarine, lard, shortening. What's the difference? Cis double bonds. The cis double bonds put kinks in the chains and make them liquid. If they're just straight chains, saturated chains, they're more likely to be solid. Okay, but now we're going to make cell membranes out of phospholipids, and most of the phospholipids out there have straight chain, saturated. Ooh, this is starting to look like a fat, or that's what the structure I would predict. If you use a lot of saturated fatty acids, you're going to make a fat rather than an oil. So our membrane is going to be more like hard butter or margarine or fat or shortening if you have a whole bunch of these chains. Wait a minute, think about like a white blood cell or an amoeba. It has to distort its cell membrane. It's distorted shape so it can move and flow and move about. A white blood cell does that too. It penetrates from the, from the circulatory system into the body to go after the bacteria or viruses, whatever have to go and gobble up. Even if you don't have that, a muscle cell's got to be part of this muscle group that contracts and moves. It needs to be flexible. It can't be like rigid like hard butter. It needs to be flexible, more fluid. So all our cells have a certain number of cholesterol molecules packed in the cell membrane, and their crazy shape, cholesterols, crazy shape, prevents these molecules from stacking tightly together. It puts a kink in the chain. I mean, this is a seriously kinked up molecule, but it puts all these weird shapes in here, keeps those greasy tails of phospholipids from stacking tightly together. This is like a lubricant. Cholesterol kind of lubes up the cell membrane, makes it more fluid, more flexible. And that's really important. If you study more biology, you'll discover that there are proteins in the cell membrane, some that go all the way through, some that sit on the surface or on the inner surface. And part of their function is to migrate through the cell membrane, so travel and get closer to the other proteins to do something. And if this is waxy or margarine or shortening, they're going to have a hard time flowing through here. No, it needs to be more like an oil, so it's more fluid, and the cholesterol is going to help lube up. It'll be stacked in here too, right? So cholesterol is amphipathic. It's got a polar head group. So this OH group sticks up with the little circles of the phospholipids, the polar groups of phospholipids. And this part's all hydrophobic. This part goes into the cell membrane with the other greasy tails. So it's too bad I didn't find a nice structure of a cell membrane with some cholesterol molecules in it, because you'd find their alcohol group would be right here, and the rest of it, how did it go? There's 3 chains, and then there's a pentagon. I forget the structure across all. Anyways, I think it's got a long tail off of here. Okay, so that's supposed to be cholesterol. It's not, but you got the idea. I hope the alkyl group is oriented or sticking to the polar head groups and the greasy tails inside. These tails can't really stick nicely to this tail, and that makes this portion of the cell membrane more fluid or oily. Cool. All right, what else is interesting or important here? I've had students ask me about LDL and HDL. If you had a blood test, you had to look at your HDL to LDL ratios. LDL stands for low density lipoprotein. Thought I had that on the slide here somewhere. I don't. HDL stands for high density lipoprotein. And just visually, you can see that the high density lipoproteins are smaller, more dense, high density. What is a lipoprotein? Well, it's got a protein, lipoprotein. There's a protein, and here it's on the top part. Inside, it's cholesterol that has an ester. So the alkyl group, which is polar, has been made less polar by changing the alcohol to an ester. And now all these greasy molecules can pack on the inside. And then on the outside, you got some phospholipids and some other things here, some proteins. And these travel through the circulatory system, transporting cholesterol. And as they bump along, the big ones are more, they have a higher chance of smashing the side of the artery or wherever the blood vessel and spilling their non-polar cargo, and this can lead to arterial plaques. Whereas the high-density lipoproteins are more compact, they're less likely to rupture. So anyways, that's what the blood test is looking at, is your ratio LDL to HDL. You want fewer of these and more of those. Fewer of the low-density lipoproteins, the one that are more likely to spill. Put all the greasy stuff on the inside of the arteries. Anything else here? Okay, LDL, HDL, non-things EM. Hope you found something interesting today. I'll see you in our final video in the next one. Take care.